Much for inviting me. Yeah, I look forward to interacting with you guys. I'm happy to take questions at any point along the way. I have more slides than I will get through. And so I guess I'll just launch into it. I changed the title here because I was asked to talk about compositionality, but the topic is actually the same as there. That was introduced. Okay, so just jumping right into it, we all know that artificial intelligence, neural nets have made a huge impact, and it continues to grow non-linearly and exponentially. And just to show an example, this is from one of the papers that was trained using an actor-critic reinforcement learning model to play one of the Atari games. And you can see that after a lot of training on the left, the model is performing really well at playing the game. And on the right, what this was an example that was made by a sort of a rival group that was not DeepMind, to show that if you only offset the paddle in the breakout by just 1 or 2 pixels, now it completely fails. So that's the kind of lack of transfer that you see sometimes in artificial neural networks that don't really amount to what you would expect from biological intelligence. Of course, there's a huge amount of progress that has been made since this work, and there's a lot of really interesting, robust in-context learning of new strategies from large language models and so forth. But nevertheless, I think we're still not at the point where those models can recapitulate all the hallmarks of biological intelligence, and especially not in the amount of training time that is exposed, that the networks have been exposed to. Moreover, what I want to, eventually get to is the kind of behavior that looks like this. Here's a guy. Okay, so you might not have expected that, but here's somebody who's producing really talented musical ability from 3 different instruments and singing at the same time, and ways that he did not actually memorize how all those things go together, but really learns these independent compositions. And we're far away from allowing artificial neural networks the ability to do that kind of thing. And of course, while this seems like a kind of special case, I think I would argue that we're doing those kinds of things all the time in real world behavior. So today I'm going to talk about sort of the brain computations that we think improve generalization and abstraction. And I'm going to go over sort of 3 different sort of examples, really a focus on the first 2, just due to lack of time. And I'm going to give a lot of them in the context of these music examples. But again, you can just think of those as high-level motivating points where our behaviors are always organized in ways that require this abstraction, generalization, and compositionality. So on the left is an example of, let's say you are a guitarist and you're learning to play different guitars, and you realize that, wait a minute, there's some superficial differences between these different guitars. But if I learn something in one guitar, I might be able to transfer that knowledge to another guitar, because what matters here is not exactly the color or the precise shape, but the mapping between which strings to play, which frets to play in order to lead to the right notes. But there may be also other guitars that have a different set of tuning, or a different, maybe it's a banjo instead of a guitar, and you might want to learn a different kind of strategy. So the idea here is that you're trying to learn from these different Cs. These are different contexts that are sort of out there in the world. You don't know what the relevant features are, but you have to learn that in order to cluster them around the latent rules. These TSs we call task sets. This is from work with Ann Collins. And so in some sense, this involves a certain kind of compositionality, in that you're separating out the surface features of the context and the stimuli and trying to learn the sort of the latent rule that then forms a group of structures that you can then reuse across multiple situations. But then I'll go on to talking about a different form of compositionality that's closer to what we saw in the motivating example of the guy playing the different instruments, where you might want to learn something, maybe you learn something on a guitar, but eventually you should be able to transfer some of that knowledge to a piano, despite the fact that the actual movements that you have to make to produce notes are completely different here. And so I will go into some detail on that. And then the last part that I probably won't get into too much is the sort of a higher level kind of deep kind of transfer, where you have to learn abstractions about tasks that you're trying to solve in ways that are not memorizing very specific stimulus action outcome combinations, but learn to sort of compress the world in a way that allows you to apply similar knowledge to multiple discrete states. So here, this is meant to represent the guitar board, and a guitarist can internalize an abstraction that realizes that all these different locations on different strings and different frets, they all might mean the note C. And once you learn that those are all equivalent, then when you learn to play a series of notes or a song on one part of the fretboard, you can then generalize it to other parts of the fretboard, and even transfer that knowledge to other guitars or other instruments of different tunings. Okay, so one of the motivating points of this in terms of inductive biases that are afforded by brains, the sort of architectures that we have that are different from maybe some of the standard artificial neural networks, is that as humans, we're often engaging in hierarchical goal, sub-goal like structure. And there are many different circuits that allow you to make decisions. So at the highest level of abstraction, in this example, maybe you're going to a coffee shop, and you're making some decision. And the decision is, should you talk to somebody, or should you perhaps go and order some coffee? And you have to make some decision at that sub-goal level. And then once you decide which coffee to get, you have to use that to constrain which reaching movement to make in order to get the coffee. So basically the point is action selection and learning is conditionalized by the higher order context. So what you're going to do here depends on what you've selected. And these are all different frontal striatal loops that go through the thalamus that involve decision-making and action selection at their own level of abstraction, but which provide contextual input to the next level down. Of course, if you're a guitar player and you're going to that coffee shop and you're wanting to sort of provide entertainment for the people there, then you may have a completely different decision to make. So in sort of more standard cognitive psychology terms, Ann Collins and I define these in terms of contextualized task sets, and I'll give some examples in terms of more straightforward experiments, where you'd have a cue that might serve as a context that would then indicate which mappings between stimulus and actions you might engage in. And so in a standard experiment in cognitive psychology, you might have different stimuli. Here we'll call S's shapes, circles, triangles, and rectangles. And then through reinforcement learning, you'd have to learn which action applies to each one of those things. Again, there's an analogy to which part of the fretboard you're using, what song you want to play in terms of which action to produce. But the point is that this set of mappings might not apply always. It's not always the case that when you see this circle, you should press action 1, but that is contextualized by a particular context, C. In this case, for convenience, I'll use C to refer to colors in the experiments that Anne ran, but that's just a convenience. It could be that these could be shapes and these could be colors. So C really means context and S means stimulus conditioned on the context. And so you can just write that in more compact form like that. And then maybe you might want to learn a whole other set of mappings between stimuli and actions for a different context. And so that every time you go to different situations, you might have to learn a whole new set of rules. And that would be, that wouldn't really allow you to transfer information very well. So instead, you might want to figure out, instead of linking directly the context to the stimulus and actions, you might want to figure out that maybe there's some latent rule that we'll call a task set that then defines what the correct set of mappings are between stimulus and action. And then the learning problem involves trying to figure out which contexts cluster around which rule and which other contexts might cluster around another rule. Also, I guess left unsaid here is that the learner also will have to figure out which features of the world constitute contexts and which features of the world constitute the stimuli that then determine the actions conditional on the context. So the point here is that this task set space is latent. It's sort of hidden to the learner. We don't know if we think about these as like different guitars. Maybe this is like one set of mappings when you're playing the guitar, and this might be for playing the banjo or the mandolin, but we really don't know how many of those there are. And so that's something that has to be learned. And yeah, this is just showing that that's the example. And so the idea that N came up with when we were modeling this 10 years ago was, well, if you visit a new context altogether, like let's say you see a new guitar or a new instrument with different colors and shapes and so forth, you could try to just learn from scratch, but it might be better to assume that the rules for that new guitar or for that new context are going to be similar to one of the rules that you've seen before, especially the one that is the most popular, the one that has the most context clustered around it. Importantly, this is not necessarily the one that's the most frequent in the world, because maybe these contexts are not observed very often. It's really about how many of them are clustered around the same context. Or you could try to choose a somewhat less popular one that might be also reasonable. And that's formalized in terms of what is often called the Chinese restaurant process prior, in which before you've observed any observations in C7, you might want to make a guess as to what's the most likely set of rules. And it just says that the number of contexts that you've seen before is going to be determine the probability that you assume that that task set applies. So you'd have a higher prior for this one than for that one. But you also have to allow for the possibility that this new C7 might require a new set of rules altogether. So that's what's called this alpha parameter, or clustering parameter. There's always some chance that you need to build a new structure altogether. And so we're using these what are called non-parametric models, where we don't assume that there's a certain number of task sets a priori, but rather you sort of building it on the fly. You might start off with one and then add new ones as needed, like this. And again, just highlighting that the task set space is not directly observed to the learner, and it has unknown size. So in that initial work, we showed that there's a Bayesian model that I sort of just alluded to that can do this problem. But we also built hierarchical neural network models that are more biologically inspired. This is just a schematic of them, in which we have context, set of units that represent context that projects to part of the prefrontal cortex, that then gets gated in through a basal ganglia mechanism that undergoes reinforcement learning in a way that is very analogous to how reinforcement learning is discussed in standard motor learning. But here, the idea is that it has to sort of select a population of neurons in the prefrontal cortex that will come to represent a task set. Initially, those neurons don't mean anything, but they will come to represent a task set by virtue of repeatedly being selected in response to a context, and by virtue of them then providing conditional input to a lower level circuit that is involved in selecting the motor response in premotor cortex. And so the idea here is that by nesting things hierarchically, the representation of an individual stimulus is going to be contextualized not only by the stimulus, but by the selected task set in prefrontal cortex. So this is sort of a layer that allows you to change your representation of stimulus depending on what you think the rule is that you're in. So like the guitar type that you're playing, or the language that you're speaking, or the sport that you're playing, those are going to contextualize how you respond to particular stimulus. And then the lower level circuit simply has to learn to select what are the right motor responses given this input. And what we showed is that if you simulate through basic reinforcement learning, you don't have any signal of what the correct task set is or the correct motor action is. You just have to do trial and error. You can simultaneously reinforce the motor actions and the task sets that seem to apply. And when you do that, when you provide the network with an old task in a new context, so you give it a completely new context, it'll learn much faster than learning from scratch, because it can simply do reinforcement learning to say, oh, wait a minute, this new context, if I just try out gating one of these representations that I've seen before, then everything I know about these representations can be immediately transferred to this level of loop. I think I'm just going to skip that. Okay, so that leads to some key predictions that we can test in experiments to see if people do it in that way. And so to do that, N designed an experiment that is really simple, where you have these different C's. You can think of these as colors or context, and S's as shapes or stimuli. But again, that's just an arbitrary assignment. And in the initial phase, all you have to do is learn that when you see C0 and S1, the correct action that's going to get you reward is A1. And when you see C0, S2, the correct action that's going to give you reward is A2. And then we structured it so that for C1, the set of actions that is rewarded is the same in response to S1 and S2. Whereas for C2, the correct actions are A3 and A4. Okay, so this is relatively trivial for a person to learn. There's just 6 mappings to learn, and you can imagine they can just learn the colored, if this is a color and this is a shape, the red triangle means A1, and just kind of memorize each different combination. But what we thought was instead, people might realize that things are structured hierarchically, and if they treat the context, the C's, as higher order, those are like, these are different guitars, and they may be able to realize that these two contexts that might not look like each other at all actually indicate the same latent task set rule. And so to test that, after people learn in this phase, we start introducing new shapes. And in those new shapes, the rules, the actions that you have to take, the subject cannot know in advance. They have to try out again through trial and error. But we preserve the fact that the state action associations in C0 are going to be the same as the ones in C1. Whereas in C2, it's a different set of action phases. So the idea is that if you had learned as a learner that instead of learning directly about C0 and C1, if you had learned that these two things indicate the same task set, then once you had learned that in phase 1, you should be able to transfer that to phase 2 so that you still need to guess here. But if you learn, let's say S3 leads to A1 in C0, on the very first trial of C1 S3, you should know that the correct action is A1. And conversely, you might see C1 S4 first, and you might have gotten rewarded for that first. And if you know that if you've done that, then on the very first time that you see C0 S4, you should also know that that's correct. So this is kind of like, again, going back to the guitar example, that you have new notes to learn, but the tuning of the guitars are the same. And one thing I just wanted to point out is that if you do this kind of training in a standard deep neural network that uses backpropagation, it doesn't actually transfer this knowledge in this phase. It doesn't have some latent structure that knows that these two things are equivalent to each other and therefore maps the new associations to that latent structure. But instead, S3 and S4 are completely different sets of units, and it's just trying to memorize exactly what to do for S3 and C0 combined. There may be, there's a lot of advances in neural networks these days, and large language models are able to extract deeper structure and make analogies, but with much more data than these kinds of models need to show that. But out of curiosity, just this morning, I ran GPT on exactly these set of associations, and I asked it to guess what would be true if you gave it a couple of examples here and asked whether it would get this one right, and it was not correct. So just an abstraction here, you would see that, what you're learning is task set 1. Task set 1 just defines whatever the state action outcome associations are. And that task set 1 continues to apply for new stimuli, even though they're different action associations. And we could then expand this transfer phase to add yet a new transfer phase, which would be giving new contexts. So this would be like giving new guitars. And there we can test, okay, if people are using structure learning and reusing knowledge, we can ask, are they faster to learn if the rules for this new context are the same as one of these previous ones compared to having to learn from scratch? And beyond that, we can also ask if it's an old rule, are they faster to learn for the more popular one than for the less popular one? Okay, so what that actually looks like pragmatically is you have, let's say, these different contexts. This TS is what is hidden to the subjects, but they should have learned that for these different shapes, A1 and A2 are correct. And now what we're doing is we're adding in a new shape and asking them to figure that out by trial and error. And then once they learn one of them, we can ask how well are they able to sort of generalize that to the other context. And then you can do the same thing for C2. And so what this is showing is that in the model, this is the non-parametric Bayesian model, but the neural network model predicts the same thing, is that initially the model is not going to be very good because it doesn't know, there's no data at all at what action to select for the diamond. But you can see that even on the very first trial, there's an advantage for the two things that have been clustered together compared to the ones that hadn't been, simply because the first trial for C0, the model might have seen C1 already. So if it learned that these are equivalent, it can generalize that. And one thing that I forgot to say is just, to make this not trivial, we made sure that when the networks or people or the Bayesian models were exposed to this task, we counterbalanced the frequency of the tasks. So C0 and C1 were each presented on 1/4 of trials, whereas C2 was presented on half of the trials. So the reason for that is to make it's not so trivial that just these associations are more frequent than those. In fact, they're just as often S1, A1, and S1, A2 are just as often correct as these ones. It's simply that there's more contexts that point to that set of rules. So on the left is the model, and on the right is human subjects from our paper. And you can see that the qualitative patterns are pretty similar, that people learn faster in the context that had been clustered together compared to another one, compared to having to learn from scratch, basically. So we wanted to test some aspects of this in neural signals. And for that, we're just going to rely on the general notion from reinforcement learning that reward prediction errors are quantified as the difference between the reward that you get and how much you expected. And so just to give you an intuition here, let's say you see this orange diamond in this situation here, and you try out button 3, and it happens to be correct. So you get a reward prediction error, and that's what it would look like. Now, the next time you see the orange diamond and you try button 3 and you get it correct, the prediction error should be smaller simply because you've learned from the previous experience and your expectation is higher. So you should have a reduced prediction error. Okay, so that's just a standard notion of prediction error. But now if we look at this, this side of the equation, if we have the red diamond and you press button 1, let's say that happens to be correct. Again, you have no reason to expect it to be correct initially, so you get a big prediction error. And now on the next trial, if you get a gray diamond, if you're not learning according to this hidden task set structure, then this is the very first time you've seen a gray diamond, so you should also see a big prediction error. On the other hand, if you have structured prediction errors where you're learning according to this latent structure, it should look like this. It should look like as if you had seen the gray diamond before, equivalent to seeing the orange diamond twice. So the idea is that you can look into the brain for looking at the signatures of their prediction errors to see if they had constructed this latent task structure and whether that is related to the degree to which they transfer. So to do that, we used a regression model where we can sort of model the EEG data from people on a trial-by-trial basis as a function of a number of terms, so just like intercept, and we can look for, are there coefficients that are sensitive to prediction errors? And over and above that, are there coefficients in the EEG that are sensitive to structured prediction errors, the degree to which the prediction errors are sensitive to knowledge of hierarchical structure? And what this is showing is that from an example electrode, FCZ, that there is the coefficient that's sensitive to prediction errors evolves over time, and there's a period early and late in the process that is significantly associated with prediction errors. And if you just want to look at where that shows up on the scalp, there's early and late components of that. It's not too critical for the points I want to make here. But what this is showing on the bottom here is that within these same ROIs that are sensitive to just straightforward reward prediction errors, both of those ROIs have additional sensitivity to structured prediction errors. So people are less surprised when the outcomes are consistent with the structure over and above what the regular prediction error would predict. So this is initially, just basic evidence that their brains seem to be sensitive to structured prediction errors. But what we wanted to finally ask before I move on to the next section is whether this structured prediction error is predicting the degree to which people are using that latent structure to transfer to new contexts. So remember, these are measured while people are learning in the initial transfer phase 1, and we want to look at whether that is indicative of this latent process that allows them to transfer knowledge to new contexts. And so what I'm showing here is individual differences. So people in blue are those subjects whose brains did respond to prediction error, but the extent to which they responded over and above that to structured prediction error is pretty much 0, so clustered around 0. And then in black, these are the individuals who had unique signatures in their brain that seemed to suggest that they were sensitive to structured prediction errors. And what we found is that if you look at the performance in new contexts, remember whether now this is the second transfer phase where they had to reuse a task set that was old before, you can see a very clear transfer that they're much more likely to reuse a task set that they had seen before compared to a task set that they had to learn from scratch. Whereas those subjects who don't seem to have structured prediction error during the prior learning phase show equivalent performance across those two new contexts. And then we can further ask the questions in the very first trial, what happens? And what we can see is that in these subjects, the ones that are reusing the previous task set, they also seem to have this prior that I was mentioning before, where they're more likely to try out the more popular task set, the one that had been associated with more previous context than task set 2, which is also an old task set. And so this is basically showing evidence that they're using that something like the Chinese restaurant process clustering prior, and that's not so much the case, again, in people who don't have that structure learning prediction errors. So a summary of that first part is that if you're doing structure learning, it leads to transfer. So people learn faster when adding new knowledge to existing structures, and they also learn faster when going to new contexts that they could reuse that information. I didn't say this too much, but I'm happy to talk about it later, there is a cost to trying to learn structure learning. So it's there's an additional credit assignment problem when you're not sure which dimensions of the stimuli are context and which dimensions of the stimuli are stimuli. And so there's actually no advantage of this structure learning in the very initial phase. But if you're willing to learn this hierarchical structure, you get benefits and flexibility and transfer later on. It depends on clustering priors, as I was mentioning, that people seem to have higher priors for the task sets that are the most popular compared to the ones that were less popular across contexts. And there are neural signatures in the brain that predict the degree to which people are transferring. And these are some other references that show some similar findings in fMRI. Okay, so that's the end of the first part. I just wanted to make sure, see if there's any questions at this point. No, I can't see anybody, so I assume that I can just keep going.
If there's any question from the audience, you can just open your mic. Okay.
No questions. Okay. So all that was nice in the sense that it shows, I think, that people are using some kind of structured learning where they're grouping knowledge from previous situations and applying it to new situations, and that you can see that in their brains. And we think that it involves particular hierarchical architectures in the brain that allow the system to do that, that aren't typically present in artificial neural networks. And it does address a certain aspect of compositionality in the sense that you're sort of separating out the surface features of the context from the latent rules. But we really wanted to start to address the sort of deeper forms of compositionality that I motivated at the beginning. So let's say you're a musician and you're learning to play piano. And then later on in life, you might want to learn to play the guitar. And these look like they're very different in terms of what you're doing, but they might share some things like the chord progression that you're trying to use and the desired sound and the song. On the other hand, if you're learning the flute and the saxophone, they also share some things that might be different, like the physical movements, the mappings, the actual movements that you're using to play these instruments have some overlap of mappings from sounds to notes. So those are two different ways in which you might share knowledge between different kinds of tasks and instruments. In one case, there's the question of what to play, which in reinforcement learning terms, we think of what is the reward function. So what is the goal? What are the things that you want to do? And for that, there might be some overlap between, let's say, the piano and the guitar. If you're trying to play the same song, you'd be happy if you produced the right sequence of notes or the right sequence of chords. But there's separately the transition function of, given that you're in a given state, what action do you need to take you to the next state? And that's what is, I'm sort of analogizing with the set of mappings here. And so if you're an astute musician and you're given suddenly a new instrument like a piccolo, ideally, if you're learning it compositionally, you would be able to realize, oh, wait, the finger mappings, the transition function that I had used before for the flute can be reused for the piccolo, but perhaps I want to use it to play a song that I had previously learned on guitar. So if you haven't done that, if you haven't played that song on the piccolo before, if you're not using compositional representations, you won't be able to do that. But if you're compositionally separating the reward function from the transition function, you hopefully would be able to do the right thing. So that's my point here, is that you need to reuse flute movements to play a song that's usually played on guitar. Or another example that we applied to a neural network is maybe you want to play the same song as you've learned before, but you decide you want to play it in a completely different rhythm. So like the bossa nova rhythm. Again, you would want to actually be able to represent those compositions. So before I go into the high level models, I just wanted to show one sort of fun example of how we applied that latter problem in a neural network that we called the AC-DC model, which stands for the Associative Cluster Dependent Chaining Model. But it's kind of fun that it has the name AC-DC based on the rock band. And the way the model looks like is that you have an input layer that projects to a recurrent neural network that's supposed to represent parts of premotor cortex, which itself develops different clusters of neurons that will come to represent elements in a sequence of musical notes that the network is trained to produce. But that whole circuit is connected to an abstraction of the basal ganglia and thalamic mechanisms that allow it to transition from one node or one cluster of units in the RNN to another. So essentially, the musical sequence order ends up getting coded in the RNN in terms of like which latent state, which order of the representations is coded in which population. But the transitions from one to the other and the timing is going to be gated by the basal ganglia, which induces activation of the thalamus, which then triggers the transition through excitatory inhibitory interactions in the cortex to the next state. And so by separating that out architecturally in the network, you can find that the model can train to learn a particular set of sequences, a particular set of notes in the RNN, but it also can learn the rhythm in the basal ganglia thalamus. And just to give a demonstration of that, one thing that one of my main contributions to this work, this was done by Chris Calderon, was to say, well, if you're going to call it the AC/DC model, you should actually train it to play the song from the band AC/DC. And so he trained it to play the introduction to Thunderstruck. If you're familiar with it, it might sound a bit familiar. Okay, so that's the sequence of notes that's applied in the introduction to Thunderstruck. And he's just plotting the RNN dynamics as a network is learning that, and the trajectory through different parts of the attractor as it's doing that. And then I'm not going to show that here, but the way the network was constructed, as I mentioned, it has this basal ganglia component that is learning timing. The network can then play that same song, but in a completely different tempo, like the bossa nova tempo, without any further training. And that's because, I mean, it would have to have learned the bossa nova tempo before in the context of other songs. But as soon as you just tell it, okay, here's the gating transitions that I want it to do through the basal ganglia in terms of the timing, it can then apply that to a song that it had learned with a different set of notes, and it can sort of combine those two things together. And then that model can reproduce various aspects of data that you see in behavior, like scalar variability, the amount of variability that people produce in response to actions that come at different times. This is a standard property that you see in timing literature, that as the desired time for selecting an action it goes up higher, the variability in time in which it's produced goes up. And then it also produces some patterns of neural activity that resemble roughly what you see in prefrontal cortical persistent activity and sequential sparse activity in the basal ganglia. Now, I didn't go into a lot of detail in this model. I just wanted to give you the gist of it, that it can do a certain kind of compositionality, but then I want to zoom back out to higher levels of abstraction. So all the examples I've given so far in terms of music for fun, but more generally, these points come up in reinforcement learning in lots of situations, especially navigation. So let's say you've learned to drive a car, and you've also learned to ride a bike. And suddenly you want to go to a place to get ice cream along a bike track or something. Ideally, you would want to be able to reuse the bike routes that you know about and the rules for how to ride a bike, the motor movements needed to ride a bike, to go to a restaurant that you've only driven to before. Right? That seems trivial. We know that we all would be able to do that. If you know the bike routes, you know how to ride a bike, you can go to a restaurant that you've driven to before, even though you've never taken these bike routes to go to that restaurant. But in order to do that, you need compositionality to separate out the reward function, which is where you want to go, from the transition function, which is what are the movements and actions and locations that you have to go in order to, get there in the right way. And so for that, we sort of break things down into the more traditional setting in a grid world space. And we're in the model-based reinforcement learning setting, where you're going to have to use the transition function and the reward function to plan how to get places. So what we did is we set up this problem for agents, for reinforcement learning agents, but eventually also for people. And we basically set up the rewards can just come from zeros or ones. The actions are the agent can go north, east, west, or south. But the actual movements that the agent has to take, the keys that it has to press, for example, in order to move in these directions, might be different. So in one context, it may have to use these particular buttons, A5 through A8, to make in those movements. But in another context, it might be other actions. And so this sort of embodies the key idea that the question is what to do. So where do you want to, what is your goal? You're trying to reach this goal, this green square here. But the transition function about exactly how you go about moving northeast, west, and south could be different. So if you take our previous model that I mentioned from Ann Collins, that amounts to something that doesn't have that ability of compositionality. It looks something more like clustering jointly the transition functions and the reward functions, right? So you would take these two different contexts, put them in their same bucket of clusters, and then that would determine jointly what transition function to apply and what reward function to apply to determine the policy. But if we want to do things in a more compositional way, we need to do something different. So Nick Franklin came up with this independent clustering model where you would still use these non-parametric Bayesian clustering agents, but you would cluster contexts that tend to go together for determining the reward function in a way that was independent from the context that might go cluster together for determining the transition function. Hopefully that makes some sense. And he tested it first on these problems that are difficult. We call them diabolical rooms problems because the agent is here. And in order to get to the reward, it has to figure out which door to go to. So it's going to go to the green door if it's correct. And if it goes to the green door, it then is in a new room. And then again, in this example, it has to go to the green door to go to the next room, and then the green door, and so forth. But the trick is that the movements that it needs to make to go north, west, east, and south in this context have this set of mappings. And in this context, it's a different set of mappings. And in this context, it could be yet a different set of mappings. And across the different rooms that the agent has to go through, it has to learn, what are the popular reward functions? So like, which doors should I go to? Should I go to the green ones or the red ones? And also, what are the most popular movements that I need to make? And it's diabolical because anytime the agent makes a mistake, so if it gets to the next room here and goes into the wrong door, we're going to make it go back to the beginning. So there's a big cost in generalization. If you're not learning things in the right way, it's going to take you a long time to get through this full thing. And so what Nick showed was that this independent clustering agent that represents things compositionally is much faster in terms of the total steps it has to take to get to the goal, compared to a flat agent, which does no structured learning at all, and also compared to a joint agent, which reflects the previous kind of model that we were working with Ann Collins. And that advantage grows as you increase the number of rooms that the agent has to go through. So this is just 3, but we went up to 40. Independent clustering leads to faster, more and more generalization. And it also grows non-linearly with the size of the grid area itself. So these were 5 by 5, but as you make it bigger, of course, it becomes more and more complex. And the independent clustering agent becomes more and more advantageous. I think I'm running close to out of time, so I'll just say a few more words. What I was just hinting at on the last slide was that it's always better to cluster things independently and compositionally, but it turns out that that's not always the case. So there are some situations in which the world is actually joints, like the reward function and the transition function do go together, and you might want to recognize that. And so Nick created some situations in which this is a situation in which these different contexts always go together with the same reward function and the same transition function. And these contexts go together with a different transition function and different reward function. So in this setting, if you want to do well, you want to cluster things jointly, because as soon as you learn about one of them, you should then transfer immediately to the other one. And so he built sort of a meta agent that would figure out, okay, this is a situation in which you might want to use a joint actor. And it sort of over time, it selects that joint actor more frequently. But you can also, of course, set up a different set of situations more along the lines of what I was showing on the last slide, where the reward functions and the mapping functions are completely independent of each other. And in that case, the meta agent should select the independent actor. And what he found was when you run this in humans, you give them a bunch of tasks online where they go through these different grid worlds, the kind of generalization that they exhibit looks more like the independent model when the previous statistics of the environment had suggested that things were independent, like the examples I was showing on the last slide. Whereas when the world was more joint in the previous statistics, the extent to which people generalize looks more like the joint clustering agent. So this is just like one summary slide. If you're curious about the details of this experiment, I would look at this paper. But this is basically showing that people differ in how much they generalize to new contexts, depending on the statistics of previous contexts and whether it seems like that world was independent and compositional or whether it was joint. And so finally, I just wanted to highlight that we can go beyond these sort of simple dichotomies of joint versus independent clustering. And there's this paper that Rex Liu in my lab had last year in artificial intelligence that showed that you can get the best of both worlds. Instead of sort of clunkily representing an independent clustering agent and a joint clustering agent and then using which one, you can actually have something that is more of a hierarchical model that in which, I guess I won't have time to really unpack it, but again, you can check out the paper if you're interested, in which the joint agent and the independent agent are actually special cases. And it can infer on the fly whether I'm in a situation that's more independent and more joint. And moreover, it also can handle exceptions, like a world in which things are largely independent, but there are some joint substructures. So I guess to be a bit concrete about that, just returning to the music example, maybe you want to transfer what you knew about a guitar to a piano. And so you might want to do that independently because what the song that you want to play is different from the movements that you want to make. But there may be specific instruments in which the kind of music that you want to play is very correlated with the movements that you want to make. Like bluegrass music is something that you tend to play on a fiddle. And so when you see a fiddle, you might want to use a rubric that allows you to represent the joint statistics there and doesn't try to, waste time figuring out what the reward function and the transition function are separately, but can just use both of those at the same time. And so Rex applied that to, again, a diabolical rooms problem, but even harder one. So here, the agent has to go from one room to the next, but in order to get from one room to the next, it first has to go through a sequence where it goes to one door, which takes it to a sublevel. So you can, I like to think of this as like Super Mario Brothers in video games, where you like go underground and you have to do something in order to get back overground. And the transition functions about how to move around in this world may or may not be similar to the transition functions of how you move around in this context, but they also may or may not be similar to the transition functions in the underworlds. And so the network has to learn the reward functions, like which doors to go to and in which order, and which transition functions to use. And it has to do all of that by going through a sequence of what we call this hierarchical diabolical rooms problem. And so this hierarchical Dirichlet process model that Rex developed learns both the covariance, which is like joint structure, and independence. So the degree to which the network can learn across these different rooms that there's a popular set of doors to go to, or maybe a popular set of sequences of doors to go to, it can leverage that knowledge, but it can also leverage the knowledge about the popularity of transition functions about how to move around and how those are informative of each other. And the long and short of it is that this hierarchical model does better than any of the other models at doing that kind of thing. This is a quite abstract and I'd say fairly sophisticated computational level model, and we still have a lot of questions about how that might be implemented in the brain and in neural networks. So there's a lot of work to be done, but it was sort of interesting. Okay, so I think I'm done. The last part of the project was about the abstractions that I said I wasn't going to have time to go through, so I'm going to just skip right away to the end here. Sorry, I should have just cut it off here. To say the summary here is that we think these hierarchical interactions between what we think is the prefrontal cortex and the basal ganglia, they support structure learning across multiple levels. So from selection of motor actions to selection of task sets and even information that goes in working memory. And when you have that hierarchical knowledge in a network, it leads to slower initially to learn action contingencies. That's the part that I didn't show, but the initial learning phase is actually slower in these models because there's a credit assignment problem across levels. But once you've learned that equivalent structure, it leads to better generalization and transfer. And we think that might actually have a role in development as to why humans, when they're learning as babies, are initially very slow at learning a lot of motor tasks, but eventually that allows them to exhibit the same kind of hierarchical generalization and transfer that we see in these models. and that which will eventually allow them to be flexible and learn languages and so forth. And finally, we talked about essentially learning to learn. So learning to learn in this context is, how do you know when the world is overall compositional, or how often is there structure where there's the knowledge about one kind of thing, in this case, the transition function, is informative about the knowledge about the other thing, the reward function. And so we need to kind of learn that across multiple environments and multiple contexts in order to know how to generalize in a new context. And with that, I just wanted to thank all the people that did this work, especially Ann Collins for the first part, and Nick Franklin and Rex Liu for the second part, and other people in my lab. And thank you for your attention.
Thank you, Michael. Thanks for your talk. It's really great. So, any question from the audience?
Hi, Michael. Can you hear me?
I can't see anybody for some reason.
Okay, very interesting talk. And so I have two questions actually. So first, in my understanding about your work is that it's mostly about the identification of the context or the state abstraction, right? And have you ever considered like put this state in some kind of sequential order and discuss a temporal abstraction rather than state abstraction?
Just thinking about that for a second. I mean, I think the grid world situations, if I just go back to the hierarchical one, that kind of is a temporal abstraction, right? Because it has to learn,
Okay.
It has to learn not only which actions to take it left, north, west, and south, but also which sequence of doors.
I see.
But I think go ahead.
Did you put planning in the in the process, like which step go or things like that, when the agent is navigating in the whole world?
Yes, and this is very much a model-based framework, so it is planning.
Okay, I see. And the second thing is that like I'm currently in Europe, and it's surprising that nowadays people are using large language model to do abstraction and things like this. And you talked a little bit about recurrent neural network, but do you think that the large language model will reframe our understanding about the abstraction in the human brain?
Yeah, great question. I have a new line of work collaborating with Ellie Pavlik, who's a computer scientist here at Brown, who focuses on large language models. And I think that there's a somewhat possible deep connection between the way that the attentional heads work in transformers, which underlie large language models, and the gating functions that we think happen in these prefrontal basal ganglia networks. So I haven't talked so much about the one aspect of this today, but we've seen in the past that these the architectures of the prefrontal basal ganglia networks that do gating can support things like indirection and variable binding, and allow you to essentially insert something into a slot of memory that then points to something else, so that you could then make novel combinations or make novel inferences that you wouldn't be able to do in a more traditional neural network. And that's exactly the kind of thing that large language models are so amazingly adept at. They do this thing called in-context learning, right? Where you have trained them a bunch on the past, but then you give them some new examples, and they're able to learn without changing their weights at all from those new examples about what kind of abstractions to use to generate the right answers. And what we're trying to understand is in more simple settings, because I think analyzing the large language models themselves is really hard. They've been trained on the entire internet, and the mechanisms that they're using, they're huge models. It's very hard to interpret, but we can still use the basic architecture of the transformer model and have it undergo different kinds of curriculum learning strategies, and try to figure out how is it able to make the kinds of transfer of knowledge that that is sort of characteristic of human behavior. And I do think that I do think we have something to learn from those models and how they solve the task. There's always the caveat that usually by the time they're able to do that really impressive in-context learning or abstraction, they have been trained on just a lot more data. So they've seen many more words than humans have ever seen before they get there. So I think there's like a trade-off between what we would call an inductive bias that is given to the brain by the architecture and the learning rule that allows you to learn to do this kind of generalization and transfer with fewer experiences versus the much more expressive and impressive abstractions that you can get from those models when they're given huge amounts of experience. And so we really want to go back and forth between those different levels of analysis to see if we could inform our understanding of one from the other.
Thank you very much.
Hi.
Hi there.
Hi, Michael. Yeah,
Yep.
That's a really impressive talk. I have a question about how people would identify context and stimulus when given a target with multi-dimension features. Yeah, like currently our tasks are mainly use two-dimension features, right? But what if the dimensions goes higher, like have 5 or 6 features? I'm thinking how will participants, identify which will be taken to context, which will be identified as stimulus. Yeah.
Yeah, no, that's a good question. I think that a neural network would have to learn. There are different ways it could learn, but one way it can learn is through these gating strategies where it sort of does hypothesis testing and it sort of gates in one of the features and reliably sort of tries that out for a while and sees how much improvement in loss it can get if it treats one of the features as context and suddenly realizes that, okay, that's the feature that I can cluster together. And when I do that, I'm going to get that much more improvement in generalization accuracy. But it would first have to try out a number of other features before it could get there. I think there's some work from Yale and Niv who's done work somewhat like that, not exactly that, but it's and I think they do have some evidence that people seem to attend to a subset of features and they might be doing it sequentially. So I think that also fits into the question of why is working memory capacity limited? Like why are people stuck to focusing on just a few number of items at a time? And we have another project on that right now where we're using some of our working memory prefrontal basal ganglia models for gating, where we give them the opportunity to sort of chunk information into multiple slots so that it sort of, because it can compress information into working memory, building on some previous work that we did in my lab that suggests that people are doing that kind of chunking. But in one of the so if you assume that there's a fixed number of things that you could attend to or hold in mind, then it's clear why chunking can help, because you can sort of free up resources for other items. But that raises the question of why not just have like larger numbers of items that you can maintain. And I don't think it's a limitation of the number of neurons or circuits that we have in the brain. I think it's a computational limitation that blows up with the curse of dimensionality. So in that work, if we just give our models many more slots, or what we call stripes, or populations of prefrontal neurons, more than it needs to even solve the task of the number of items, more than the number of items that it needs to consider, those models actually do worse. And that's because if you don't have a supervised signal that tells it, okay, here's the right representation in pre-FC to use for the task, it has to try out many different ones and has to figure out which item should I put in which slot, and at what moment in time should I read out from that item and slot in order to that slot in order to make the right response. And that leads to this huge credit assignment problem that blows up. So the idea is that the reason we have to focus on just a few things at a time is that allows you to solve the credit assignment problem in a sort of sequential way until you achieve sort of like an aha kind of moment.
Yeah, thank you. I think that selective sequential learning will be a great solution, and I'm considering maybe inductive bias can facilitate this process. Like, when we are faced with different features, inductive bias can tell us which features should go first, right? And especially in some cases, when there are two features have same performance, like two features can be both as context, maybe we can use inductive bias to select which one shall we rely on in the future. Yeah.
Yeah, that's great. I mean, I think that also fits into this idea of clustering priors. The answer that I just gave you was in the case where we have no priors, but if you have a reason to think that one feature is more likely to be relevant for a higher level context than another, then you should certainly use that inductive bias to as a prior, essentially.
Yeah, cool. Thank you.
You're welcome.
Thank you for the talk. I may ask a question that's sort of related to the previous question, which is whether you believe in the task you ran on human participants, were the humans explicitly thinking about the strategies to use on which dimension to attend to, and if you have tried instructions that will help them use these strategies so that they can pick up your task more quickly, or expose specific priors they may have.
So you're asking that if we give them instructions about, for example, what are the contexts and what are the stimuli?
Yes, or any instruction, or what kind of instructions do you think would be best to understand for your models and for testing your hypotheses? Like whether it's just learn by trial and error.
Yeah, I mean, I think we were interested in this work anyway, of not biasing them too much, because actually in the original paper with Ann Collins, we didn't have that case where there's two different contexts that meant the same task set. We actually set it up in a way where that there was actually no incentive at all to construct a task set. So there was just C's and S's, and the subject could decide to use the C, the color, as the high level context, or they could decide to use the shape as the high level context. And neither one would help them for initial learning. But then we set up a transfer phase such that if they had used the color as the high level context, they would immediately know how to generalize to that new color. And the idea behind that was to say, even in situations where there is no obvious structure in terms of which dimension is high level and which is low level, do people spontaneously generate that structure? And it looked like they did, because we had like independent measures of whether, so in cognitive psychology, if people are using one dimension as a task, then when that dimension switches, they get switch costs. So we could look at when the color shifts from one trial to the next, how slow are the reaction times, and look at that asymmetrically from when the shape changes from one trial to the next. And so what we found is that in the setting where there's no bias whatsoever, so no instructions and also no bias even in the task structure, the people who had more of a switch cost when you switch the color compared to switching the shape, those are the ones that actually showed generalization in the transfer phase when they could generalize based on color, and vice versa. If you set it up so they could generalize based on shape, then if they had a higher switch cost in advance, they would do so more like that. And we did a follow-up EEG study that suggested the same thing, that you can decode from their EEG which dimension of the stimulus they're treating as higher order. So we were explicitly trying to not give them instructions, just to see to what extent people, when they're learning simple learning problems, are they sort of biased to search for hierarchical structure, because we think that kind of bias is a form of an inductive bias that then allows you to learn in a reliable way that transfers and generalizes. That said, I think you can still give instructions in some situations and still show you still show switch costs for sure. If you were to tell them to use color as a high level context, then they would show the switch costs, and then they would be more likely to show transfer based on color later on. And I guess, yeah, we have another line of work in which you do give people instructions in more basic aspects of reinforcement learning, and it does give them, it influences what they learn in a way that is consistent with kind of a confirmation bias, right? So the instructions in some sense have too much effect on their learning. But yeah, that's a different line of work. So I think my general answer is that we're just interested in what spontaneous strategies people take when they're learning a new task. To what extent do they tend to use structure? To what extent do they tend to use working memory without trying to bias them one way or the other?
Thank you very much.
And we have a question in the chat box. Hello, Frank. I'm still confused about the balance between compositionality and structure. Do you explain how it works in the neural network?
Okay. I guess the question is whether that is, there's two different neural networks, or there's the one, for some reason it's asked me to share my, so I'm going to go back to the, so in this neural network, there's compositionality in the sense that the network learns in their RNN, it kind of learns which populations to activate at which element in the sequence through learning, right? So it's got given some input, it has to learn to produce a set of actions that would be like producing a set of notes. And the only thing that this RNN learns is that, you know, which population to activate in response to which order in the sequence. But the reason why it's compositional is that the learning mechanisms down here are mechanisms for triggering the transitions from one cluster to the other. And that, I guess I don't have the plots to show it, but some of them are in the paper in terms of dynamics of these activities. They sort of ramp up to a certain level in terms of once there's enough activity in the striatal go units, they will trigger a transition to activate a thalamic unit, which would then trigger a transition in the RNN. And because the learning mechanisms here are sort of independent from the learning mechanisms here, you can, it exhibits compositionality at the level of rhythm. So you can learn like the bossa nova rhythm or some other musical rhythm here in one task, and then just reapply it in that same, in a new task or in a new sequence but in response to this input layer, which would tell it, you know, what sequence to present now. And then it would combine those two things, that this thing would tell it what sequence to present, and then the input to this network would tell it what rhythm you want it to play, and it can combine those two things together. And it can scale up the sequence. It could make it slower or faster, make it synchronous or isosynchronous. So that's, I guess, the gist level description of how it can do compositionality in this network. But if you were asking about, this one, so this model can balance, it optimizes the trade-off between structure and compositionality in a very abstract sense. So this is a non-parametric Bayesian model that learns clusters, and we don't actually have a neural network that implements this yet. This is something that I've been wanting to build for a while, and I think it's challenging. And well, I don't know how challenging it is until we try to build a neural network to see if it could replicate some of that structure of balancing the when it should use joint structure versus when it should use compositional structure. I guess one thing that I can say is that in earlier work with David Better, which is somewhat related, he had tasks where people had to learn either hierarchical learning tasks, where it required using these hierarchical gating mechanisms in the prefrontal cortex that we could model its learning of this sort of really rapid transfer of hierarchical structure. But then he also had a condition where there were 3 different dimensions of the task, like color, orientation, and shape. And in one version of the task, it was completely just conjunctive and joints. So there's no hierarchical structure you could use. So in that model, the way we modeled that was it would use reward prediction errors to gate the prefrontal cortex hierarchical gating strategy. But if that was not worthwhile, if it was not working because the task was not actually hierarchical, it would exhibit a lot of negative prediction errors and it would stop gating in the prefrontal cortex. But then it can still use the hidden layer. So it's just a straightforward multi-layer perceptron to learn the conjunctive joint strategies to then determine the outputs. So that is, I guess that is one sense in which you can balance compositionality with joint structure by saying you have one network that tends to search for hierarchical structure that is in a sense compositional. And when it learns that it's not the right strategy for the task, it can then rely on this more joint structure. But it didn't, it doesn't solve all the kinds of problems that this network solved or that this model solved. Does that help?
Oh, thank you, Michael. Lastly, I have a question. Conceptually, how do you integrate the role of replay or hippocampus into the hierarchical framework you mentioned, like the frontal striatal circuits?
Yeah, that's a good question. I think of there's a number of ways to think about that. So one is that we tend to think of the hippocampus circuit as being able to learn, episodic memories of conjunctions. So along the lines of what I was just talking about, if you want to, instead of just have some low dimensional representation of stimuli in some sensory input layer that projects to the basal ganglia, you could also have a hippocampus that would represent very specific conjunctions of features that are almost like special cases that could also feed into the gating process for deciding, okay, what action to select based on this specific conjunction. So kind of like the hidden layer I was talking about before, it could be done more reliably with a hippocampus that is really good at doing pattern separation and so forth. But a more interesting aspect of it, I think, is the last part of the talk that I didn't go through. We have started to think about how you can learn, use hippocampal replay to learn abstractions. So if you, let's see if I can, actually, one thing, maybe I can just present one picture without going through the details of all this stuff. So, and this is work by Alana Jasker in my lab, who's working on this experimentally. So let's say you've experienced something in the past where there's a different set of, there may be a different set of sequence of notes that you've presented that all indicate the same reward function. And you want to basically look at, okay, these are all equivalent to each other. Initially, when you're learning guitar or learning any new skill, you would have to kind of memorize the rules for each different aspect of it. Okay, when I press the C here, it sounds like this. When I do this, it sounds like that. But during replay at night, you might want to have a mechanism that would learn the reward predictive sequence. So it would learn, okay, here are all my hippocampal representations. This is abstract here, but let's say the hippocampus is representing these transitions, as other people have speculated, between states, actions, and subsequent states, and possibly rewards. And if it turns out that there's a whole number of hippocampal states that all are related to the same reward predictive sequence, so they're all related to, if I take a certain set of actions in this state, I'm going to get the same set of sequences of rewards. I may not have taken those, I may not have been in those states at the same moments in time, but if they all have the same reward predictive sequence, then at night, there's we think possibly a part of the brain that tracks these reward predictions, the sequences of rewards, and that it would reactivate maybe randomly sequences of rewards that would then reinstate all the hippocampal representations that were associated with that same sequence of rewards. And so by doing that sequentially, because you're sampling from the reward predictive sequence, you would be reactivating hippocampal representations sequentially that had not been experienced sequentially during the day, but they mean the same thing in terms of reward sequences. And that will allow the cortex to learn to represent those as all equivalent. So it allows it to learn this abstraction so that you can then transfer that abstraction to new instruments. So I'm not sure if that was, I mean, I didn't go through the rest of this part of the talk, but the gist of it is that the hippocampus in this case is learning very specific associations like it always does in lots of models of the hippocampus. But we're leveraging the idea that you can replay those hippocampal memories. And if you replay them together, temporally structured, that could allow the cortex to learn a similar representation for these very different hippocampal representations if they mean the same thing in the context of reinforcement learning. Does that make some sense?
Yeah, thank you. So, is there any other question?
Hello, I have a question about the compositionality and the and about this one. From this picture, I think this is about cortical columns structure, right?
I'm sorry, I didn't hear that last part.
From this picture, I recognize similar to the cortical columns structure. Is it a spiky neural networks to model the cortical columns, or is it just how do you represent the normal artificial neural network about the memory SASR?
Oh, I see. Well, this here is actually just a schematic of how we think it might work. We haven't actually built this model yet. We've built more tabular, or yeah, we built these reward predictive models that allow it to generalize using successor features. It's just that the algorithm that is needed to sorry, I'm struggling a little bit here because I didn't go through the prior work that motivates this, but the algorithm is essentially says that when you're learning in a new situation, you have to use the full high dimensional state space of whatever you think the task is, because you haven't been able to compress it yet in any useful way. And so the hippocampus is what we would imagine would represent that high dimensional state space, where like every point in space or all the different features of the world are represented separately, and then you learn what actions to select in response to those. But then offline, you could then realize that certain states mean the same thing, that they are associated with the same sequence of rewards if you take the same policy in those states. And so in the actual computational models that we have done, we have an offline algorithm that learns to figure out of all the states that it's seen in the past. It does well, there's different algorithms for doing that, but one of them uses gradient descent. It figures out how can I minimize the loss on that I would get from just compressing all the representations, so that maybe let's see if I can go through a little bit of it. Yeah, so this is a very simple demonstration. So let's say you have this column world where you're in a grid world and the ones are the rewards. Initially you need to represent the full high dimensional state space because you don't know where the rewards are going to be or where the actions are going to be. But you could realize eventually that you can just compress this whole state space into one row, because you don't need to know the differences between the different columns, because the correct policy to get the reward is the same no matter what column you're in. You just go right and you're going to get the reward, right? So the original problem would look like this, but the compressed problem would look like, okay, well, I'm taking the same actions, and here I would just be revisiting back to the same sort of latent state in this problem. So the action sequence looks like that, and the latent state sequence looks like that, and the reward sequence looks like that. So of course, compressing it to this abstract problem only works once you've explored this environment enough to realize that all the columns are equivalent to each other. And so when we apply this kind of algorithm to more complex problems, we find that the compression allows it to generalize to new situations without having to know the transition function or the reward function. It just generalizes the abstraction. But in order for that to work, it has to first consider the high dimensional representation and only do the compression offline. And so that's what's motivating our thoughts about replay, because it does the compression offline, whereas online, when you're first learning the problem, you might want to use the hippocampus. I just don't have time to go through the whole logic here. But if you're interested, the relevant paper here is this one, where we're using reward representations. It's just that we didn't implement that in terms of a hippocampus or anything like that. We just speculate, I think, in the discussion about how it might relate to replay. And what we're currently working on is with Alana, the grad student I mentioned at the end, is showing that humans seem to have transfer that is consistent with this reward predictive representations, and it may benefit from sleep. So that's what we want to test. And then we want to implement that in actual neural models that might involve something like the hippocampus. But the schematic that I showed you at the end was just like a cartoon for now.
Okay, great. Thank you.
Oh, thank you, Michael. So if there's no question, it's about time. It's overtime, actually. So thank you again, Michael, for your impressive talk, and thank you all for listening. So that's it today.
Okay, thank you so much for having me.
Thank you.
Now I can see you.
Bye.
Okay. All right, bye.